Okay, good morning, everyone. Today we'll go over the rest of the theory for AC analysis problems, and on Friday we'll wrap up the chapter with solved examples. Okay, so let's section 3. We stop right here. Okay, any questions about any of the material we have covered so far? Are we clear on the terms? Yes. Sure. One time period. Well, if you just want the base, then it's just one time period. But yes, it's the time that we're interested in or analyzing. But typically, it's just one time period. Did I cover this or not? The RMS relationship between RMS and the magnitude. Okay. One thing I would point out is if you've seen VP-P or VPP, that stands for peak to peak. You're measuring from the maximum value to the minimum value of the waveform. And so typically it's 2 times the peak value. So it's 2 times VP or 2 times VM. Okay. So if you're trying to find the RMS value from a peak to peak value, then you would take VP-P divided VRMS would be equal to V peak to peak divided by 2 root 2. Okay. So if you have a peak to peak value, you would divide it by 2 first, get half to get 1 peak, which is VM or V peak. And then you divide it by root 2 again to obtain the RMS value. Okay, so why do we use sinusoidal? Well, the first and the most important reason is that it's very easy to generate. Sinusoidal voltage and currents are very easy to generate. You have a coil that is rotating, mechanically rotating inside a magnetic field, which has a north and a south pole. And so when the electrons come out, the shape of the current and the voltage is sinusoidal in nature. It goes to a positive peak, north pole, goes back down to the negative peak, north pole, south pole, north pole, south pole, and back and forth. And so they are very easy to generate. Mathematically, they are very easy to handle. The the derivatives and integrals of sinusoids are also sinusoidal in nature, right? Sin x and cos x. The result is cos x and sin x. And then again, speaking mathematically, if you perform Fourier analysis, then any periodic waveform, doesn't matter what shape it is, rectangular, square, triangular, sawtooth, ramp, arbitrary noise, can be represented as a sinusoidal waveform. Okay. And so many things in nature are also sinusoidal in shape. So again, why sinusoid? Well, those are multiple reasons why we use sinusoidal waveforms for AC analysis. All of the power in our, that comes to our homes and commercial spaces, that's all sinusoidal. Okay, again, it's very easy to generate and distribute. So similar to DC, AC also has a steady state voltage and current. That's the thing that we're analyzing, right? That's the response that we're analyzing. So when you apply a source voltage or current to a circuit, the circuit itself is not AC or DC. It's the application of the source that makes it an AC circuit, right? A resistor, inductor, and capacitor, they are the same. The response depends on whether the source is DC or AC. So if the source is DC, then we call it a DC circuit. We use DC circuit analysis techniques. If the source is AC, then we say the circuit is AC circuit, and we perform AC steady state analysis. So the response of the voltage or current for an inductor, capacitor, or resistor to the application of an AC source results in an AC steady state response. And we will solve for that AC steady state response. So we look at the voltage, the current in that circuit. Okay. Now, we saw in chapters 3 and 4 how if we want to solve for the voltage and currents, we need to solve differential equations. And again, if you're anything like me, it's not my idea of a good time. That's not something I like to do. So fortunately for me and for you, is that there is a solution to that. And it is representing the AC source and the components using complex number math. So we use complex math to make the math less complex. And what we do is we represent both the sources as well as the components as vectors. And we use real and imaginary numbers to do that. And what that does is it allows us to apply all of the DC circuit analysis techniques that we learned in chapters 1 and 2 to AC circuits. For instance, in chapter 3, we learned about the voltage for an inductor and the current for a capacitor. Because VL is, anyone remember? L di over dt, right? Voltage for an inductor is L di over dt. And then in chapter 4, we learned about differential equation. Well, when we do a transform and represent it using complex number math or complex numbers, we don't have to do that anymore. We can simply apply Ohm's law and find voltage using IL times ZL. That's it. We do simple multiplication from the inductor current and the inductor impedance, but the quantities are complex, so complex numbers. And we do that by representing it as complex quantities known as phasors and impedances. Okay, phasors and impedances. So differential equations are reduced to simple circuit analysis problems. Simpler. Okay. So again, phasors and impedances are complex quantities represented by complex numbers. These phasors, unlike the ones from Star Trek, are not going to stun or kill you, but they will scramble your brains a little bit. Sources are represented with phasors. Inductors and capacitors are represented as impedances. So let's look at both. First, we'll look at phasors, then we'll look at impedances. All right, phasor is nothing but a rotating vector in the complex plane. Okay, this is the time domain expression, right? We have a waveform that has a different value at any given point in time. It's a function of time on the x-axis. It's rotated. It's rotated. Just for illustration purposes, okay? It's rotated just for illustration purposes. So again, x-axis is time, and this quantity, whether it's voltage or current, has a different value at any given point in time. The shape is sinusoidal in nature. The representation, mathematical representation, uses sine or cosine, right? Sine or cosine. So we already saw this equation last class. V of t is represented as Vm cos of omega t plus or minus theta. Three quantities that describe this waveform in the time domain. One is the magnitude or the peak value, the frequency, and the phase. The reason we keep the phase separate is because we want to perform a phasor transform and represent it as a vector in the frequency domain. Okay. And what does a vector need for its description? Magnitude, direction, right? So by direction, we mean the phase angle in degrees. So one full rotation of the vector is 360 degrees, which equals one full cycle in the time domain. One full cycle. Or radians, it's 2 pi. One full cycle means one positive and one negative cycle. One time period. So it's in the frequency domain, it's one full rotation of that vector, 360 degrees. So this is the positive half cycle. This is the negative half cycle. Each half cycle is pi. So one half cycle is pi, or 180 degrees. Now, coming back to this illustration right here. As I said, the phasor is a rotating vector in the frequency domain. It's rotating at a speed of omega, but it does not require omega to describe it. We only need the length, and we only need the phase angle it makes with the real axis, which is right here. The length is Vm, or the magnitude. Hence, this author likes to use m as a subscript. Even though we typically use peak or peak values, the book that I use uses m because we describe the time domain expression as a rotating vector with the length equal to the magnitude, Vm. As a reminder, Vm is again the peak value, Vp. Okay, so if you take a different class, if you read a different book, this expression might be written as V of t as Vp cos omega t plus or minus theta. Again, exactly the same thing. All right, so what is this vector? This vector is a single snapshot. Okay, it's a single snapshot. It's showing you one moment in time where the waveform crosses the x-axis, which is right here. And this goes here. It's the length of the vector when it crosses the x-axis. Okay, and the distance away from 0, 0 gives you the phase, represented by the phase angle of that vector right here. Okay, again, it's a single snapshot. The vector, that phasor is a vector that is a single snapshot of a moment in time of that time domain waveform. Okay, if that time domain representation crossed the x-axis at 0, 0, then the phase would be 0. Theta would be equal to 0. The vector would be lying flat on the real axis. The phase angle would be 0. Make sense? Right? So the two things that describe it is basically Vm and the phase angle theta. And that's it. So if you wish to do a phasor transform and describe it mathematically as a vector, all you would need to do is extract information about the magnitude and the phase, and that's it. But one important thing to keep in mind, I mean, there's math involved in this. There's a derivation, of course. So one important thing to keep in mind is, if you wish to do this, the equation or the description or the expression must be in cosine. Or the phasor transform. So if you are given an expression, V of t is sine omega t, omega could have any value, sine omega t, then you have to use the expression sine x is equal to cos of x minus 90. You have to subtract 90 degrees from the expression. It becomes cos of omega t minus 90 degrees. And then you can directly write down the phasor. Phasor for this would be 1 with a phase angle of 90 degrees. Okay. All right, let's take a 10-second pause. Let me know if you have any questions. Yes. So that's just kind of my notation. This is in the book. So it's, it's kind of like inclined with the left side of the V much thicker than the right side. So I guess it's easier to show it in the book. I simply use, there's kind of like two horizontal marks on top of that V. And so I just use that to indicate that it's a phasor. Oh, oh yeah, 1 with a phase angle of minus 90 degrees. That's it. So magnitude 1 and phase angle minus 90. The theta value is minus 90. Yes. So it's pointing down. The vector is pointing down. Minus 90. So plus 90, you would be rotating counterclockwise. So positive phase angle is counterclockwise. Negative phase angle is clockwise. So instead of going counterclockwise, you're actually going, instead of going counterclockwise for a positive phase angle, you're going clockwise. So minus 90 would be pointing straight down. Yes. No, we don't need to. We keep it separate for this specific reason because we need to perform a phasor transform. So you're talking about this one? Yeah, it's a phasor. The phasor does not include any frequency information. There's no omega in there in the description. Again, remember, it's a vector. Vector needs only magnitude and phase angle. That's it. Minus 90, to come back to you, one more point about that. Minus 90 can also be written as plus 270. Both would be exactly the same. So either you go clockwise and you get minus 90, or you go counterclockwise and you get plus 270. So one full circle, 360 degrees. Yes. No, one is just because there's nothing there. So the amplitude or the magnitude is 1. Good questions all. Yes. No, no. The value of omega does not matter at all. Online, if you're gonna write something in the chat, yeah, let's do pi, then it's shoot that. Theta can also be given in radians, cos omega t plus or minus theta. No, we keep theta separate, and the reason is because we want to write the phasor diagram directly. So the question being asked is, why is theta not given in radians? Why is it given in degrees? And the reason is we want that phase or the phase difference to describe the vector phase angle. That's why we keep separate in degrees. It is, of course, possible to combine it. We can convert it into radians, but we don't. 360 degrees is 2 pi, so we can convert it from there, but we don't. Yes. Yes. It's simply from there. So it's not listed, it's just 1. And so VM or VP is 1. And that's where that comes from. Yeah. But again, the equation must be in cosine, right? Trigonometric identity forms a right angle triangle. So opposite upon the hypotenuse, that's where it comes from. When you do a phasor transform, there is again a derivation that goes along with it. Yes. Mm-hmm. So minus 90 would simply be pointing straight down. That's all it would look like if you plot it. It's a rotating vector. The vector is just pointing down. That's all it's doing. No, VM has no effect on that. VM is simply the length of the vector. That still stays the same. You cannot describe this as a phasor. If you want to describe this, then it has to be in cosine. All we're doing is subtracting 90 degrees from the phase angle. Right now, the phase angle is 0. So theta is equal to 0. But it could be like 78. It could be minus 97. It could be anything. If it's sine of omega t minus 97 degrees, for instance, then it would become cos of omega t minus 187. Yes. That's it. One point in time. It's just describing it one point in time. All right. Any other questions? We have time. Okay. So that was for the sources. Now let's talk about the components. Impedance. Impedance comes from the word impede, as resistance comes from resist, right? Resistance is basically the opposition to the flow of electrons, opposition to the flow of current in a circuit or in a component. Similarly, we have the concept of impedance. Impedance, like a phasor, is a complex quantity. We use complex numbers to represent it. And it has a basis in real life, okay? Impedance for a resistor, inductor, and capacitor is what we will use to convert our circuit for circuit analysis, okay? All right, so the complex quantity impedance is represented by the letter Z. Letter Z. It has two parts to it. The real part is represented by resistance R, and the imaginary part is represented by the reactance X. Now, when I say real and imaginary, I'm referring to the mathematical representation, okay? Reactance and resistance have a basis in real life. They have a physical basis in real life, okay? Reactance comes from the fact that the inductor and the capacitor are energy storage devices. They store energy in the form of a magnetic field or an electric field, okay? So these fields give rise to a voltage that opposes any change in the input voltage or the input current. For instance, we apply an input current to an inductor. That input current will cause a voltage to appear across that inductor. Ignore steady state conditions and all of that. But when you apply an input current to an inductor, it causes a voltage to appear across that inductor. It sets up a magnetic field. That magnetic field gives rise to a opposing voltage. That voltage polarity is opposite of the initial voltage that is generated due to that input current. Okay, it causes an opposing voltage, and that opposition is represented by the reactance. So it has a physical basis in life. It is real, but mathematically we represent it using the imaginary number. Okay, we represent it using the imaginary number. So anytime you hear the words or read the words which says imaginary reactance, it is talking about the mathematical representation. So always be aware of that fact. Okay, it's talking about the mathematical representation. As a side note, the imaginary number in electrical engineering is represented by J and not by I. Okay, I is used for current, and so we use J. So again, impedance Z is a complex quantity. It's a sum of the resistance and the reactance. The resistance is represented by the real numbers, and reactance is represented by imaginary numbers. Imaginary number J in electrical engineering. So R plus JX. And again, you can transform this as a vector which has magnitude and phase angle theta. Okay, magnitude and phase angle theta. Impedance, yes. So impedance is a complex quantity. It's simply the sum of the resistance and the reactance. All words are kind of synonyms of each other. Impedance, resistance, and reactance are all representing opposition. It is opposition to the flow of current, opposition to the voltage, opposition to any change in the input voltage or any change in the input current. Okay. If the current or voltage is constant, inductor becomes a short circuit, capacitor becomes an open circuit. But anytime you change that input current or input voltage, there is an opposition to that change. And that is represented by the reactance. And again, to make calculations simpler, to make calculations easier, we use imaginary numbers. And so we use the term imaginary reactance. But again, that's a mathematical reference. Okay. Imaginary reactance is a mathematical reference. The concept's clear? Okay. All right. The symbols are exactly the same, and so are the units. All represented as the same symbol that we use for resistors, and we use ohms for all three. Impedance, resistance, and reactance are all the same. So from this, from the short few sentences I talked about impedance, what is the impedance of a resistor? Remember I said impedance comprises of resistance plus reactance. Reactance is due to the electric fields and the magnetic field that is set up in a capacitor and an inductor. So what is the impedance of a resistor? It's the resistance itself, because it is R plus J0. So it's simply the resistance itself. There is no such thing as the impedance of a resistor because it doesn't have any reactance. It's simply the resistor itself. Remember the words, resistor behaves exactly the same way it does for DC as well as for AC. It simply opposes the flow of current and causes a voltage drop to appear across it. ZL, however, does not have any resistance. An inductor, an ideal inductor, does not have any resistance. It is supposed to be a short circuit, 0 ohm resistance. Okay. And when we perform theoretical analysis, all components are ideal. Resistors are ideal, inductors are ideal, capacitors are ideal. So ideal inductors do not have any resistance, R equals 0. And it's the same for a capacitor. This actually is minus JXC. Minus comes from the fact that it's 1 over J. It's the reciprocal of J. XL is omega L, also equal to 2 pi F. Omega is 2 pi F. Omega is the angular frequency or the angular velocity in radians per second. And the equation that governs, that relates it to frequency in hertz is 2 pi F. So 2 pi FL, And XC is 1 over omega times C, which is 1 over 2 pi FC. Again, all of these equations, you can have them handy on your equation sheet, but you should be able to use them to solve for the voltages and currents. Okay. So ZL is J 2 pi FL, ZC is 1 over J 2 pi FC. The reciprocal of the imaginary number is the negative of the number. Does everyone know that? 1 over J is minus J, hopefully. Okay, let's see. So when you transform this into polar coordinates, you get omega L with a phase angle of plus 90 degrees. For ZC, it's 1 over omega C with an angle of minus 90. There's a reason for that, which I will explain in just a little bit. Again, rectangular coordinates versus polar coordinates. It's a complex quantity. So if you plot the vector, you get what is known as an impedance triangle. Impedance triangle. Okay. Where resistor R, again, is on the real axis. Reactance X is on the y-axis. And you join the two ends together, complete the triangle. You get what is known as the impedance triangle. Impedance triangle. With a length equal to magnitude of Z with a phase angle theta. You can see it for a resistor, right? Resistor X is equal to 0, so the impedance is lying flat on the real axis. So ZR is equal to R. For an inductor and a capacitor, it's lying straight vertically up. Actually, for an inductor, it's up 90 degrees. For a capacitor, it's down 90 degrees. But we good so far? Any questions? Okay. All right. So remember, I talked about phase difference between waveforms, right? Leading and lagging. So in a capacitor and an inductor, actually, let me write it here. The voltage and the current are not in phase. They are out of phase by 90 degrees. In an inductor, the voltage leads the current by plus 90 degrees. And in a capacitor, the current leads the voltage by plus 90 degrees. So for an inductor, if you're performing the mathematical operation for impedance, again, similar to resistance, if we apply Ohm's law, we can write ZL is equal to VL or IL, which gives you theta V minus theta I, which gives you plus 90 degrees. Plus 90 degrees. I'll explain about the mathematical operations in the next few slides. But for now, just know that we apply Ohm's law and we can find the impedance, or we can use impedance the same way we did resistance. And so if we do that for capacitor, the capacitor voltage and capacitor current are also 90 degrees out of phase. But in this case, voltage lags the current for a capacitor. And so the phase angle or the impedance is minus 90 degrees. And hence minus j omega c, or minus j1 over omega c. That is specific to all inductors and all capacitors. If you take any inductor, any capacitor in any circuit, the phase difference between the voltage and current for that particular component is always 90 degrees. It could be 78 for the voltage, the current would be minus 90 of 78. So it'd be minus 78, what, 12? Minus 12. It would be 135, minus 135. Difference would always be 90 degrees. Okay, so the value could be anything, but the difference between the two will always be 90. Voltage for an inductor is plus 90 with regards to current for that inductor, and voltage for a capacitor is always minus 90 with respect to that capacitor current. Okay. So what is the purpose of doing all of this? Well, I'll come back to this slide later. The purpose of doing all of this transformation into complex numbers is so we can apply all of the laws that we have learned so far. If you think mesh current analysis was fun in chapter 2, how about we use complex numbers to do mesh current analysis? That sounds like a lot of fun for Saturday night. Yeah, don't worry about it. I'm not going to ask students to do mesh current or node voltage analysis or superposition using complex numbers. We learned the techniques, right? We learned the techniques in chapters 1 and 2. Then we explain the concepts in this chapter, and we'll look at several problems, but most of them will be the level of performing like Ohm's law or KVL or KCL, not anything more than that. Okay. Because once you have the concepts down, the math is something you would encounter in your own fields. Okay? This math is not something that is unique to EE. Some of you may have already taken classes where you've done this kind of math, perhaps even advanced than this. If not, there'll be some classes in your future where you will do this. So it's not specific to EE. Okay, so Ohm's law. Remember I said for chapter 3, in chapter 3, voltage for inductor is L di over dt. If you wish to find voltage for inductor, this is the equation we would use, right? Chapter 4, we wrote out a differential equation. If we wish to find inductor current, we would integrate the voltage. We won't have to do any of that. We simply transform the circuit, represent sources as phasors and components with their impedances, and we simply apply Ohm's law. V equals IZ. If we talk about just the RMS values, then you could also use V equals IX. Reactance, right? We don't take the phase numbers into account because we're talking about RMS values. So V equals IZ, V equals IX, they all apply. Ohm's law applies as it did for chapters 1 and 2. KVL, KCL, they all apply exactly the same. All the techniques that we learned, mesh current analysis, node voltage analysis, superposition, everything applies exactly the same way as we learned in chapters 1 and 2. And that is the beauty of using complex number math. Okay, differential equation problems are reduced to simple circuit analysis problems. So VR is IR times R, VL is IL times ZL, and VC is simply IC times ZC. Now, this is the point where I inform the students that you need to be an expert or at least adept at using your own calculator devices to perform complex math. Okay, using complex numbers. My calculator is from excuse me. My calculator is from the 90s, specifically 1992 when I first began. And so, oh yeah, really, it still works from 1992. So it doesn't have any fancy programmable functions in there. but I can perform complex number math by transforming polar coordinates to rectangular and back and forth. So I can do some complex math, but not much beyond that. Nowadays, you have the TI-80 series, TI-83, 84, 85, I think. But we would not be able to help you how to use it. So you need to work, or you need to practice how to do that on your own devices. Everybody has different ones, but most of those models are more or less the same. So if you don't know how to use it for complex math, you need to practice. There is a practice workout sheet that I have on the website. Download that, and go through the practice problems, and well, become skilled and adept at using that. It will be helpful to you. If you've not done it so far for any of your classes, it should be helpful in the future. It'll definitely be helpful now. So what I do is I need to transform back and forth between polar and rectangular coordinates, perform math operations. Again, a vector which has a length of r and a phase angle of theta can be represented by its projection on the x and the y-axis as a real as well as the imaginary component. So r with a phase angle of theta is a plus or minus jb, right? So mathematical operations we will perform, addition or subtraction, is easier if you have rectangular coordinates. Multiplication and division is easier if you have polar coordinates. Oh, I heard there's some fluids midterm or something today. How many of you have that? If y'all need to study, that's fine. I've heard that's always a rough one. Okay, so addition and subtraction, we would want rectangular coordinates. The reason is you could simply take the real parts and add or subtract, and then take the imaginary parts and then add or subtract. So if it was two numbers like this, you would simply add or subtract the real parts. So it would be a plus or minus c, and then the imaginary parts would go together, b plus or minus d. Right? And then if you are multiplying, then it's easier to do it in polar coordinates. So let's say you have a number a with a phase angle of theta b, and you try to multiply it with c with a phase angle of theta d. The magnitudes are multiplied, a times c, and the phase angles are summed up, theta b plus theta d. If you're performing a division, same principle. Magnitudes get divided, but the phase angles are subtracted. Numerator minus the denominator, theta b minus theta d. So for me, if I was trying to solve a circuit and I have, let's say I'm applying Ohm's law and I'm multiplying two quantities, voltage times, current times resistance. So if one of those quantities was in polar coordinates and the other one was in rectangular, and I want to perform a multiplication, on your devices, you could plug in the numbers as they are and it would spit out an output value, right? Easy enough. For me, what I would have to do is transform the rectangular coordinates into polar, perform the multiplication manually, and then find out the answer. Positives and negatives of both is that if you do this manually, then you have to go step by step, but chances of errors are minimized. Versus trying to input the big long equation into your calculators. If you make an error entering even one quantity, your entire answer would be incorrect. So positives and negatives of both approaches. But again, you need to be adept and skilled at using your own calculators to perform these math functions. Just one or two more slides and we are done for today. Any questions about anything we have done so far? Okay. Let's see, fundamental laws, impedances in series and parallel. Yes, very important. Two more slides. So if you have an inductor, you can represent it as an impedance, right? L is represented as ZL. If you have a capacitor, you can represent it as ZC. Now, inductors and capacitors, we already saw how they add up. If you combine the value of the inductances, you can add it up either in series or parallel. Capacitors also. But if you have an inductor and a capacitor together, you can represent it, of course. Actually, let's draw it down here. So L and C, if they come up in our circuit, I can represent it as two impedances. The connection still remains the same, so it's still series, becomes ZL and ZC. I can find the total equivalent impedance between the outer terminals. And impedances add up the exact same way that we add up resistors, whether in series or in parallel. Okay, so we cannot combine inductors and capacitors as they are because two different components. But the impedances, yes, we can combine those. So ZEQ in this case would simply be ZL plus ZC. Again, take note of the fact that we are not combining the inductor or the capacitor. We are combining the impedance of the inductor and the capacitor. Okay, so ZL plus ZC is the EQ. We are not talking about L and C, but ZL and ZC. It's an important distinction. So they add up the exact same way as you add up resistors in series and resistors in parallel. A parallel combination of impedances is simply the reciprocal of the sum of the reciprocals. So 1 over Z1, 1 over Z2, and so on and so forth. Impedances in series are simply added up or summed up. And this will be very useful. Again, remember the whole point of doing all of this transformation is so we can analyze the circuit as if it was a DC circuit, right? The only difference is that we now have phase angles to take into account. Yes. Yes. Well, reactance is basically the imaginary portion. So if you have it in rectangular coordinates, that's the imaginary portion. The reactance is there. Once we have the numbers, then it's simple math from that point on. So then we don't worry about whether it's, whether it's reactance or whether it's resistance or whether it's the phase angle of the phasor. It's just math from that point on. And then finally, these are terms that you will not see in this class, but it's something that you should still be familiar with. And you would have seen this in the lab. If you took the lab in lab, I'd say 6, I believe. No, 6 or 7. 7, I believe. Anyway, these are simply reciprocals. So impedance comes from impede. Admittance, the reciprocal of impedance is admittance, admit. Resistance comes from resist. Resist the flow of current, resist the flow of electrons. Reciprocal of resistance is conductance. So you permit the flow of electrons, or you permit the flow of the current. And then reactance has a reciprocal, which is susceptance. So they're all reciprocals of each other. Z is 1 over I. Sorry, I should go back. Z is 1 over Y, which is admittance. G is conductance, and B is susceptance. So 1 over Y, 1 over G, and 1 over B. The unit for all three is the same. Impedance, resistance, and reactance is ohms. So admittance, conductance, and susceptance is Siemens, named after the German physicist. Can't remember his first name. but it's Siemens. The reason it's useful is this. If you have a parallel circuit, as we just saw here, you have to take reciprocals twice. So before we had powerful calculators in the palm of our hands, we had to do everything manually. So it makes it easier to perform manual calculations if you simply take the reciprocals of your components. So if you have the reciprocals, then you can simply write in admittance is the sum of, let's say it was ZL, ZC, and R in parallel, it would simply become Y is equal to GR plus BL perhaps plus GC. Okay, you simply sum it up. So YEQ, which is the reciprocal of the impedance, right? If it's connected in parallel, you have to take the reciprocal anyway. So Y would be equal to GR plus GL plus GC, just the reciprocals. So makes it easier if it's a parallel circuit. But nowadays, of course, we have powerful computers, powerful calculators, so it doesn't make too much of a difference. All right, well, I'll end class here today, and we'll pick up here again on on Friday for all the 5 examples. Homework 15 was due tonight. I shifted it to Thursday night tomorrow, but that homework is based on the material that we covered on Monday, not today. So, and it's mostly short answer questions, concept based, so you shouldn't have much difficulty with it. Reach out to me if you need any help. All right. See you all on Friday. And good luck with your midterms.